Hello, my dear students. Welcome to ESR chemistry classes. Here we are in lecture number 5 on ESR spectroscopy. In this video, we will discuss hyperfine splitting. The most common feature of ESR spectra is their hyperfine structure. It means the ESR signal consists of more than one fine lines, and this type of a structure of ESR signal is called hyperfine structure. The splitting of individual lines of ESR spectra into components is called hyperfine splitting. Let us see it again. The splitting up of individual lines of ESR spectra into various components is called hyperfine splitting, and this phenomenon it causes hyperfine structure in the ESR signal. The hyperfine structure of ESR signal is produced due to hyperfine splitting. Cause of hyperfine splitting. The hyperfine splitting arises due to magnetic interaction between the unpaired electron spin and the magnetic dipole moments of nuclei with nuclear spin non-zero present in the radical. If the free radical species contains some nuclei whose nuclear spin is not equal to 0, then magnetic interaction takes place between the unpaired electron spin and the magnetic dipole moment produced by such nucleus. If only magnetic field acting on unpaired electron were that of external magnet, if the magnetic field which acts on the unpaired electron is only that of external magnet and the strength of this magnetic field is B, then the ESR spectrum would consist of a single line with the frequency specified by the G value. Let us see it again. If only external magnetic field acts on the unpaired electron, its ESR spectrum should consist of a single line. However, the spin of unpaired electron also interacts with the magnetic moment of any nucleus with nuclear spin not equal to 0 in its vicinity, in its neighborhood. The spin of unpaired electron also interacts with the magnetic moment produced by nearby nucleus with non-zero nuclear spin. As a result, the single line of the ESR spectrum, of electron splits up into a sets of 2i plus 1 lines by this hyperfine interaction. If the unpaired electron of a free radical comes in the vicinity of a nucleus with nuclear spin I, then the single line of the ESR spectrum due to this unpaired electron splits up into a set of 2I plus 1 lines, hyperfine lines, due to this hyperfine interaction, and it produces hyperfine structure in the ESR signal. It is obvious that the hyperfine splitting and hyperfine structure of ESR signal arises due to interaction of a spin of unpaired electron with the magnetic moment produced by nearby nucleus with non-zero nuclear spin. ESR spectrum of hydrogen atom. The hydrogen atom consists of one electron with S equals to half. A spin quantum number is equal to half, and one proton with nuclear spin also half. The hydrogen atom consists of one proton with nuclear spin half and one electron which also has a spin angular momentum quantum number equals to half. The proton is also a source of magnetic field which depends on the direction of its nuclear spin. The spinning proton is also a source of magnetic field, and this magnetic field depends upon the direction of nuclear spin. The magnetic field of the proton, the magnetic field produced by the proton adds to or subtracts from the external magnetic field. If external magnetic field of a strength B is applied on this unpaired electron, which is in the vicinity of a proton in hydrogen atom, the magnetic field experienced by the electron may be greater than or smaller than the applied magnetic field, because the magnetic field of proton may add to or subtract from the external magnetic field. Let us illustrate it. The local magnetic field experienced by the electron in hydrogen atom can be given by the local magnetic field experienced by the electron in hydrogen atom can be given by the expression B local is equal to applied magnetic field plus HAMI, where B is external magnetic field which has been applied, H is Planck's constant, and M is nuclear or angular momentum quantum number, A is hyperfine coupling constant. It may also be denoted by capital A. We know that for a proton I is equal to half. For a proton I is equal to half, and the value of Mi may be plus half or minus half. Case 1. If Mi is plus half, then the local magnetic field experienced by the electron will be greater than the applied magnetic field, because Mi is plus half. This value will add to applied magnetic field. In case 2, if Mi is minus half, this term will become minus, that is the local magnetic field will be smaller than the applied magnetic field. Thus, the electron of hydrogen atom placed in an external magnetic field of strength B experiences two different local magnetic fields depending upon the nuclear spin of the proton. The electron may experience higher or lower magnetic field than the applied magnetic field. Therefore, the energy of an electron in the vicinity of a nucleus with nuclear spin I in an external magnetic field of a strength B can be given by the energy of an electron which is in the vicinity of a nucleus with nuclear spin I in an external magnetic field of a strength B can be given by the following expression. E is equal to G beta B ms. This is the energy of electron in magnetic field if it is in the free state. It is not in the vicinity of any nucleus, and this term has been added due to magnetic field experienced by the spinning proton plus HAMIMS. The two energy states of a free electron in a magnetic field are ms equals to plus half and ms equals to minus half. For a free electron in a magnetic field, there are two energy states, ms equals to minus half and ms equals to plus half. This has lower energy while this one has higher energy. For each value of electron spin angular momentum quantum number ms, for each value of ms of electron, the nuclear spin angular momentum quantum number, that is mi, can have two values, plus half and minus half. For each value of ms of electron, mi can have two values, plus half and minus half, and according to this equation, there are four energy levels for an electron in hydrogen atom in an external magnetic field. It can be understood as follows. For an electron in hydrogen atom, S is equal to half and ms may be plus half and minus half. I for the nucleus of hydrogen atom is half, and accordingly mi will also be plus half and minus half. For each value of ms of the unpaired electron, mi can have two values. If ms is plus half, mi may be plus half or minus half. Similarly, if ms is minus half, mi may have plus half or minus half value. Therefore, there are four energy levels for an electron of hydrogen atom in an external magnetic field, which can be given as follows. Depending upon these facts discussed, there are four energy levels for an electron of hydrogen atom in an external magnetic field of strength B as discussed below. Four energy levels of an electron of hydrogen atom in an external magnetic field of strength B. We have seen that the energy of an electron of hydrogen atom in an external magnetic field of strength B is given by E is equal to G beta B ms plus HAMI ms. If ms has value 1 by 2 plus 1 by 2. If the value of ms is plus 1 by 2, the mi can have two values, plus half and minus half. If ms is plus half and mi is also plus half, then the energy of electron will be ms is equal to 1 by 2 g beta b plus ha. Mi is plus half and ms is also plus half. And if ms is plus 1 by 2, mi may be minus half. And in this case, the energy of electron will be E2, 1 by 2 G beta B plus HA. Mi is minus half, while ms is plus half. If ms of electron has value plus 1 by 2, mi can have two values, plus half and minus half, and accordingly there are two energy levels for electron with ms equals to plus half. On the other hand, if ms is minus half, mi can again have two values, minus half and plus half. If mi is minus half and ms is minus half, then the energy of electron will be E3. The value of ms is minus 1 by 2. The value of mi is minus half, and this is the value of ms. On the other hand, if the value of ms is minus half but the value of mi is plus half, the energy of electron will be E4. ms is minus half, this one is ms, and mi is plus half. Thus, if ms of electron has value minus 1 by 2, mi can have two different values, minus half and plus half, and it is obvious that there are four energy levels, E1, E2, E3 and E4 for an electron in hydrogen atom in an external magnetic field of strength B. These four energy levels of an electron of hydrogen atom in an external magnetic field can be given in simplified way as follows. E1 is equal to 1 by 2 G beta B plus 1 by 4 HA on solving the expression for E1. Similarly, E2 is equal to 1 by 2 G beta B minus 1 by 4 HA. E3 is equal to minus 1 by 2 G beta B plus 1 by 2 HA. These expressions are obtained by solving the previous expressions, and E4 is equal to minus 1 by 2 G beta B minus 1 by 4 HA. It is obvious that E4 has minimum value, both terms are negative, while E1 has the highest value because both the terms are positive. The energy of these four energy states of electron in hydrogen atom in magnetic field increases in the following order. E4 is minimum, followed by E3, E2 and E1. E3 is greater than E4, E2 is greater than E3, and E1 is greater than E2. This is the increasing order of energy of four energy states of electron in hydrogen atom in an external magnetic field. E4 has the minimum energy while E1 has the highest energy. On comparing E2 and E3, it may be seen that the first term dominates over the second term. Here the first term is negative and the second term is positive. Here the first term is positive and second term is negative, and therefore E2 is greater than E3 because the first term dominates in deciding the energy of the energy state. It is greater than 1 by 4 Ha. Thus, the energy of four different energy levels of an electron in hydrogen atom in an external magnetic field of strength B increases in this order. The ESR spectrum of a free electron consists of one signal. This single ESR signal of free electron splits up into two lines. In the case of hydrogen atom, as a result of the interaction of electron with the proton. The ESR spectrum of free electron consists of only one signal, but the single ESR signal of free electron splits up into two lines in the case of hydrogen atom due to interaction of the electron spin with the magnetic moment produced by the proton. This phenomenon is called hyperfine splitting, and it produces hyperfine structure in the ESR signal. Hyperfine splitting due to a single proton, two signals of same intensity are obtained. Hyperfine splitting due to a single proton. If hyperfine splitting takes place due to a single proton in hydrogen atom, two signals of same intensity are obtained as illustrated below. The value of S for electron is 1 by 2, and the value of Ms will be plus half and minus half if there is no magnetic field. Ms equals to plus half and minus half have the same energy, and that is these two spin states are degenerate. But if an external magnetic field of a strength B is applied, the spin state Ms equals to minus half has lower energy, while Ms equals to plus half has higher energy, and the energy difference between these two spin states of electron is G beta B. And this transition between the spin states of electron takes place by absorbing suitable frequency from the electromagnetic spectrum, producing one ESR signal. Only one ESR signal is obtained for a free electron in magnetic field due to this transition. But magnetic field plus magnetic field effect of one proton under the influence of external magnetic field plus magnetic field effect of one proton, the energy states are 4, E1, E2, E3 and E4. E4 corresponds to Ms equals to minus half and Mi equals to plus half. E3 corresponds to Ms equals to minus half and Mi equals to plus half. Similarly, E2 corresponds to Ms equals to plus half and Mi equals to minus half, and E1 corresponds to Ms equals to plus half and Mi equals to plus half. These are nuclear spins. If Mi is equal to plus half, the nuclear spin is represented in the upward direction. On the other hand, if Mi equals to minus half, the nuclear spin is represented in the downward direction. There are 4 energy levels for an unpaired electron in hydrogen atom under the influence of one proton, E1, E2, E3 and E4. Two transitions are possible among these four spin states of electron of hydrogen atom in external magnetic field. This transition takes place from E3 to E2 and the energy difference between these two spin states is delta E1. On the other hand, the second transition takes place from E4 to E1 and the energy difference between these two energy levels is delta E2. This amount of energy is required for this transition while delta E2 amount of energy is required for this transition. Please note that these two transitions involve delta Mi is equal to 0. This transition takes place from Mi minus half to Mi minus half, that is delta Mi is equals to 0, and this transition also involves Mi equals to plus half and Mi equals to plus half, that is delta Mi is equal to 0. Here too the ESR signal splits up into two components in the case of unpaired electron of hydrogen atom in an external magnetic field. Energy required for two transitions of electron from lower energy spin state to higher energy spin state in hydrogen atom in magnetic field. We have already seen that two different amounts of energies are required, delta E1 and delta E2. It is obvious that the energy required for these transitions involving delta Mi is equal to 0 can be given by delta E1. We have already explained that delta E1 is equal to E2 minus E3. It is the value of E2 and it is E3. If E3 is subtracted from E2, then delta E2 is equal to E1 minus E4. On putting the values of E1, E2 and E3, E4 in these expressions, on solving these equations, we have delta E1 is equal to E2 minus E3. If this quantity is subtracted from this one, it will become positive and it will become negative, G beta B minus HA by 2. Similarly, delta E2 is E1 minus E4. If E4 is subtracted from this amount, we get this term will become, if E1 if E4 is subtracted from E1, this will become positive and this will become also positive, and accordingly delta E2 will be G beta B plus HA by 2. This will become positive. It is already positive. 1 by 2 HA, 1 by 4 HA plus 1 by 4 HA will become plus HA by 2. It is obvious that this transition requires a smaller amount of energy than this transition. The energy required for this transition is G beta B minus HA by 2, while this transition requires energy G beta B plus HA by 2. This is higher amount of energy, while this is lower amount of energy. ESR spectra of free electron and hydrogen atom in the presence of external magnetic field. This is the ESR spectrum of free electron in magnetic field of strength B, which is increasing in this direction. If dA by dB is plotted against B, a single signal for free electron is obtained. This is a single signal for free electron in an external magnetic field. But if this unpaired electron is present in hydrogen atom in magnetic field, this single signal splits up into two hyperfine lines. This is the ESR spectrum of electron in hydrogen atom in magnetic field. This single signal splits up into two hyperfine lines, and the spacing between these two hyperfine lines is nothing but hyperfine coupling constant, which is denoted by a small a or capital A. The hyperfine splitting in many other cases will be discussed in the next video. Thank you for watching the video with concentration. Please like and share it, and if you have not subscribed my channel yet, please subscribe it so that you get information regarding my new videos in time. Thank you again.